Hi, yeah, thank you everyone for coming. My name is Mark. I was recently a visiting researcher at Meta where this work was done. So today I'd like to talk about Tectonic-Shift, which is a composite storage fabric for ML training at Meta. So to begin with some background, the Tectonic file system serves as the durable storage foundation for pretty much the vast majority of Meta services. So within a data center, we have a number of tenants ranging from blob storage, so images, videos, et cetera, all the way to data warehouse serving AI applications. So these applications communicate and store data within Tectonic using a client library, which communicates with a metadata layer to perform metadata operations, and of course stores data within a linearly scalable chunk store composed of hard drive-based storage nodes. There's a number of background services that operate on these Tectonic components, but for more information, please check out the previous paper on Tectonic. So Tectonic was really great at, for our needs, really scaling to exascale within a data center. But this was until recently when one of our applications really experienced an explosion in demand, right? And this, as you can imagine, was these AI applications. And so this is really a symptom of this industry-wide shift towards needing to train these larger, more complex models, such as LLMs, and largely in our case, these deep learning recommendation models. And specifically, what we need are two things from ML infrastructure, right? We need scale-up infrastructure, meaning that historically, we've trained models on CPUs, we've moved to GPUs, and even more recently, at ISCA, we talked about our own ASICs, right, for our models. And so not only is each chip getting faster, right, we need more chips. So we need scale-out infrastructure. Again, historically, we leveraged single node training. We're able to use a single server. We moved to racks, and now we have these data center scale AI training clusters composed of tens of thousands of these accelerators training a model. So kind of all of this combined, right? What does this mean for storage? Well, we've seen a huge explosion in read IOPS demand for these ML data sets. As you can see to the left, over the course of about 2 years, this IOPS demand has more than quadrupled. And what this means for infrastructure in terms of storage is, as I'm showing on the right, for a lot of our models, the capacity that we're provisioning for storage for storage servers is equal to how much we provision for GPUs for these trainers, right? So this is an immense amount of capacity for storage. So really the question that we started asking a few years ago was how do we scale Tectonic to meet these exploding IOPS demands, and how do we do it efficiently, right? So we really started off with a hardware design space exploration. And if we think about kind of the capacity, what we need from the hardware, we need two things. One is we need enough storage to store the bytes. And secondly, we need enough IOPS capacity in terms of read bandwidth, right? And so we considered a few options. One option was pretty straightforward, put more hard drives in Tectonic's chunk store and scale it out that way, so the status quo. So what I'm showing in this table is normalized power requirements first to meet storage requirements for bytes, right? Secondly, to meet IOPS power requirements for read bandwidth. And last, what we really need is to meet both, right? So obviously we want to be lower here, but as you can see, we are over-provisioning our storage capacity by an order of magnitude, in this case, to meet IOPS demands than we would to simply store the data sets themselves, right? So there's this huge imbalance between what we can offer in terms of storage versus IOPS using just Tectonic. So naturally, you may think, okay, Flash is a bit more IOPS efficient. Why not just put everything in Flash? So this is a bit better, but it doesn't solve the problem. You can see we still have a similar symptom here, right? Where we have this imbalance because Flash is less dense, we're now storage bound. We have to provision more Flash drives to store the data set as opposed to serving IOPS. So naturally, the solution that we ended up pursuing was this notion of composite storage, right? So if we just wanted to store the data set itself, we would use hard drives, right? They're very dense, they're very cheap. If we wanted to serve IOPS, we would just use Flash, for example, if we didn't want to care about storing the bytes, right? But really, we need to meet both requirements. So let's use each device to its own strength, provision hard drives for storage requirements, and whatever's not covered in terms of IOPS by those hard drives, let's provision more flash to cover those demands. And so that's why here it's not exactly the sum of the two requirements. We have a discount in terms of hard drives are able to cover some of the IOPS requirements here. But you can see the takeaway here is that, overall this efficiency is much, much better than what we were using before. But it's not as simple as just buying a bunch of hard drives and a bunch of SSDs and provisioning them in our data centers, right? We really need to think about how we design the software around specifically this flash tier to maximize how much IOPS it absorbs without storing the entire data set. So the good news is, as we show in the paper, we performed an extensive workload characterization of our data sets. And what we saw is that our data sets do have this skewed popularity distribution, which makes it amenable to caching. So the x-axis is for one of our production data sets, the bytes of that data set ordered by read popularity. The y-axis shows the total percent of storage IOPS that those bytes contribute to. So the takeaway from here is that you can see that the majority of our IOPS can be served by a quarter of the bytes in storage. The bad news is that our ML workloads are so different in terms of the access patterns compared to your traditional cache workloads, for example, CDNs, social graphs, et cetera, right? So current caches are really ineffective at just capturing data reuse for these jobs. As you can see in the figure here, what I'm showing is over 600 production ML training jobs reading one of our data sets over the course of about a week. And each line is the duration of that job. So kind of to summarize here, what our ML jobs look like are they're massive scans. They scan over 10 to even 100 petabytes of data. They run for hours, if not many days. And on top of that, they're single epoch, meaning that they read each sample once and they don't repeat samples. So there's no data reuse within a single training job. This results in a lot of this antagonistic churn pattern, right? So data reuse is across these training jobs. They're very highly asynchronous. They're multi-tenant. A bunch of users are training on a data set at once, if not a bunch of teams are training on a data set at once. So if we were to just deploy a general purpose LRU cache, this would result in a ton of thrashing, rendering it pretty ineffective. More recent ML-specific caches largely focus on kind of capturing data reuse within multi-epoch jobs or single-tenant environments or hybrid parameter tuning jobs, which aren't really fully representative of our workloads. So it was really clear to us that we needed to build a flash storage tier designed specifically for what industrial ML workloads look like. And so that's why we decided to build Shift, which is a transparent and application-aware flash tier. So Shift is designed around 4 key design principles. First, we specifically designed it to be transparent to end users. So, a ton of services across Meta use the Tectonic API. We didn't want them to know that even Shift existed, right? We expose the same API, the same semantics, the same guarantees that Tectonic exposes to applications. But at the same time, as I'll go into detail a bit later, we need to understand how applications behave and use information that the applications can provide to us to maximize IOPS absorption. We designed Shift to be simple. We build directly on top of Tectonic's metadata layer and use CacheLib, which is an internal or a caching engine developed at Meta. And finally, it's scalable and fault tolerant. We use a decentralized and DHT-based architecture. So by combining Tectonic with Shift, we have Tectonic-Shift, which is Meta's production ML storage fabric. So what does it look like, right? Within a data center, we have your standard Tectonic cluster as before, but now we have this additional Shift cluster, right? This cluster is composed of flash-based storage nodes arranged in a consistent hash ring. Within each storage node, we have a CacheLib runtime managing both DRAM and flash. And then your training job still uses the Tectonic client library as before, so same API. But now internally within this within the client library, we perform a check if each read is cache eligible. So cache ineligible reads will default to reading from the Tectonic cluster as before, nothing changes. So these maybe would be, for example, non-ML jobs that aren't really IOPS bound. For ML jobs, we will perform a cache lookup into the appropriate storage node based on the hash. And if there's data there, we'll return a cache hit, and the training job will use that data. If it's a miss, each storage node will check if that data should be emitted to cache. If not, then we'll return a miss, and then the job will fetch data from the Tectonic cluster by default. If we do decide to emit it, we'll fetch, the storage node will perform a fetch to Tectonic to bring that data into CacheLib and insert it into CacheLib. So it's an emission policy. This may cause some eviction, and we have this additional similar policy where we evaluate if we should re-emit that evicted data back into CacheLib. So this architecture is pretty straightforward, as you can see. But the key here really is we need to implement these cache policies on top of CacheLib, specifically tailored for our ML workloads, that is able to maximize how much IOPS each storage node absorbs. So that's really the goal here, is to maximize IOPS absorption. And quickly, at a high level, walking through how these emission policies work. First, for each read miss or eviction, we'll categorize that data into a specific bucket. So buckets represent some commonality in the data. For example, a training table partition or a feature within our data set. Dynamically, we'll prioritize these buckets based on either I guess both, either or both, historic signals, or as I'll talk about later, we can derive the future accesses of each of these training jobs from the data set. And then based on each bucket's priority relative to this emit threshold, we'll decide to emit it into CacheLib or reject it from cache. And this threshold is designed to avoid cache thrashing and also manage flash endurance limits. So you can see that kind of the key here is how do we calculate these priorities, right? And so first we have this traditional, whatever cache uses, which is this notion of historic accesses. So we take a log of recent requests to each bucket and use this idea that past popular requests are indicative of future popular requests. But really the key insight here is that we're able to know what the future is for a lot of our workloads. And specifically, as you can see to the right, once an engineer launches an ML training job, they specify what the data set is, right? So what the table is, what the rows and what the columns within that table that they want to read throughout the duration of the training job. And so by mapping down the semantic information down to bytes that are stored within Tectonic, we effectively are able to kind of get this oracular schedule, right? We know what each training job will read in the future throughout its lifetime. And we're able to use this to tune these bucket priorities. So again, for example, if we've seen a lot of recent requests to a specific bucket, or if we see that there's a lot of pending requests or active jobs that will plan to read a given bucket, we'll prioritize that bucket higher over other buckets. And it's not just the bucket priorities that we tune dynamically, we also adjust this threshold. So we have some minimum emit threshold where we reject buckets, but if we also see that, for example, CacheLib has a very high flash write rate, we'll adjust this threshold to be a bit higher to limit that write rate to an acceptable limit for our flash drives. And so really the key here is that by dynamically adjusting these emission policies, the bucket priorities, the threshold, we're able to keep high priority data in cache, so data we think will be used frequently in the future, while minimizing the antagonistic patterns I talked about before and addressing flash endurance limit concerns. So kind of putting this all together, by kind of mapping each of these reads to a bucket, we're able to capture the spatial locality of our training jobs, right? By dynamically adjusting the priority of each bucket, we're able to capture the temporal locality of these reads, and then this threshold is dynamically tuned to avoid thrashing our cache and to avoid burning out our flash drives. So I want to quickly go over some evaluation results. So first we started looking at, we evaluated Shift using a benchmark, which consists of 3 production DLRM or recommendation model training workloads on a testbed Shift cluster. So we compared first against CacheLib's eviction policy, so LRU and FIFO. What this table shows is the normalized I/O absorption across these benchmarks normalized to LRU. So we want it to be higher is better here. First, we configured Shift with a historic admission policy, which calculates these bucket priorities from just past access information. And it's on top of LRU eviction. Secondly, we configured a future admission policy, which uses the future accesses derived from this dataset specification, again on top of LRU eviction. And then finally, we have a hybrid policy, which takes the max of the bucket priorities calculated from either the historic or the future admission policy. So the takeaway here is that by using these intelligent shift policies on top of CacheLib, we're able to significantly increase the IOPS absorption over the baselines. It's not just about IOPS absorption. We also need to limit our flash write rates, as I talked about earlier, in production. So for evaluation, we set a 100 megabyte per second average write rate limit. And here, what I'm showing is we compared against the baseline. In this case, it's CacheLib's dynamic admission policy. So CacheLib will randomly decide to reject reads to flash such that it meets this write rate limit. So the first row here, again, is the I/O absorption. Higher is better. The second row is the write rate limit normalized to the limit. The NVM write rate normalized to the limit. So we want to be around or below 1 here. So we also compared against CacheLib's reject first policy, which rejects the first writes of each object to flash, and also just an omit all policy, which omits everything to flash. So you can see that these policies increase I/O absorption over the dynamic emission of CacheLib, but at the expense of significantly much more write rate such that it exceeds our limits. Meanwhile, all of the shift policies, again, outperform in terms of I/O absorption, the baselines, while also meeting our flash write rate limits. So Shift has been deployed into production at petabyte scale across many data centers since early 2022, and it saves significant amounts of storage infrastructure power. So what I'm showing here is a production trace of one of these clusters over the course of 9 hours. The baseline in blue is this expert-tuned emission policy, which just emits high IOPS tables to cache. Shift with using intelligent policies is in orange. And then the y-axis is normalized I/O absorption, normalized to the point that we need to be power neutral, right? So anything above 1 saves power, anything below 1 loses power because we have to provision power capacity for these nodes, right? So you can see here that Shift is able to save 29% of power in this case relative to just using hard drives, so the status quo I talked about before. And if you consider this at petabyte scale across many data centers, this is a massive amount of power savings. So just to conclude, what I talked about is that what we've seen industry-wide is this trend towards scale up, scale out ML infrastructure, right? And if we think about what that means for the storage infrastructure, we need to meet these massive and exploding IOPS demands. We designed Tectonic-Shift specifically to meet these demands by combining each tectonic cluster with a flash-based shift cluster. It's designed to maximize how much IOPS it absorbs using a suite of intelligent policies, leveraging both historic information, but also future accesses derived from application semantics. And it currently serves as Meta's ML storage fabric and has saved significant amounts of storage power across multiple data centers. And yeah, thank you so much for your time. Happy to take any questions.